Section 7.2, trig integrals. Before we begin, let me go ahead and recall some notation, mainly exponents of trig functions. So we have, for example, sine squared of x. That means we're squaring an entire trig function, our sine function. So it would be the same as sine of x squared. However, not to be confused, it is not the same as sine of x squared, which is the same thing as sine of quantity x squared. So when we're working with these, if you see yourself getting caught up with the exponents, you can take that exponent on the trig function and apply it to the entire trig function in parentheses if you see that that's more helpful for you. Okay, let's begin. In this section, we use trig identities to integrate certain combinations of trig functions. We start with powers of sine and cosine. So why do we need an entire section to work with trig integrals? Let's blindly try the following example. Our example reads, evaluate the integral of cosine cubed of x dx. And if you need to, you can always rewrite it as cosine of x cubed dx. And as you see, we're going to use, this would be an example where you need to be careful with your chain rule, right? So let's say if you're working with chain rule, you're going to use some type of u substitution, then what should u be? You can say, okay, well, u should be cosine, but then the derivative, we need the derivative as well. So the partial derivative of cosine is sine of x dx. And notice we don't have a sign. So notice that using substitution in chain rule might not be the best step yet. So then we have to work on this problem a bit more cleverly to get what we want. So is there a way to use trig identities so that we can introduce a sign? Let me write this. Can we introduce so we need to introduce a sign so that we can continue with our u substitution. Since we know we have a cubic, we're going to have to incorporate or make up that exponent of 3. Okay, well, why don't we split cosine cubed? Why don't we go ahead and take our cosine cubed of x and split it to a cosine squared times cosine. Now, this way I can introduce a sign because I can go ahead and use our Pythagorean identities. And remember that sine squared of x plus cosine squared of x equals 1. So I can replace cosine squared with 1 minus sine squared. So let's go ahead and do that. So to write our integral, we're going to split it to a cosine squared and a cosine squared and cosine. We're going to replace cosine squared with 1 minus sine squared of x times cosine of x dx. And now we're in a position where we can go ahead and use our u substitution. And we have to think about what would be the best option for our problem. Now, this didn't work, right? So let's take a look at our new integral problem. Well, we know the derivative of sine is cosine, and sine is that something that's in parentheses squared, right? So that would be our ideal u. Now I'm emphasizing this because in the beginning I had labeled something else as a u, but that was a totally different setup for integrals that we were thinking of. Okay, so we're going to let u be sine of x, since that's our quantity squared, and our derivative of sine, our partial derivative of sine is cosine of x dx. Let's go ahead and use that u substitution. So we have our integral of 1 minus, we have our u squared, times cosine dx, we said that's du. All right, now we can go ahead and integrate. So that we have u minus u cubed over 3 plus c. We replace our u so that we have sine of x minus 1/3 sine cubed of x plus c, since that was our u. So taking a look at our introductory example, we see that there's a lot more to these problems. Now, everything you need to know to move forward, you kind of already have it under your belt. It's just a matter of knowing how to think to get through these problems. Now, as we proceed with this section, have your cheat sheet with trig formulas handy. That will be very helpful. And just in case you didn't run to go get them just yet, I have them with you. To emphasize some that we're going to use the most, we have our Pythagorean identities. It might be helpful to use our even and odd functions. We can go ahead and use our product to sum identities, depending on our argument. And we can also use our double angle identities when we don't want something squared or want to get rid of the exponent. That would be helpful. All right, so everything is really fair game, but those are the ones that we typically see a bit more. Now this cheat sheet is from the back of a textbook. The author is Leo. It's by Pearson in the trigonometry textbook. I just used this one because it was more condensed. Let's go ahead and do another problem. So we have find the integral of sine to the 5th power of x cosine squared of x dx. So let's make a note. As we're going to work with this problem, we're going to keep in mind that the derivative d dx of sine of x equals cosine of x. So we want to make sure that if we're integrating and they're being multiplied, remember we can think of them as separate integrals if they're adding, but if they're multiplied, they have to work together. So we need to make sure we have a sine, a cosine in our setup to be able to integrate. All right, we need both sine and cosine. All right, so we know that the derivative of sine is cosine, and our problem here is our exponents. So I know I can get rid of that sine by using our Pythagorean identities, but I only can use them with an even exponent. So that leaves an extra sign left over. Well, that's okay, because I still want to have a sign in the story. All right, so I'm taking my sine to the 5th power. I took one out, and so I'm left with sine to the 4th power. Let's go ahead and write it as sine squared squared. So I have sine squared squared. Now I can go ahead and replace it using my Pythagorean identities. So sine squared is 1 minus cosine. So 1 minus cosine squared of x squared. We have cosine squared of x, sine of x dx. Okay, now we're in a good position to use some u substitution. Okay, for this case, since our cosine is the argument that's being squared, That should be our u. So I have u equals cosine of x. And the derivative of cosine is sine. So our partial derivative of cosine is negative sine of x dx. Okay, notice we don't have a negative sign. We have just positive sign. So I need to incorporate a negative, and when I need to incorporate another negative, because a negative times a negative is a positive, and that way I didn't actually change the value of my integral. Okay, so we see that here we have our du. We replace our u's, so we can write our integral to be negative 1 minus u squared times u squared du. Now it's just an algebra problem. It looks kind of like we need more work to do, but don't get caught up with all the different integrals you learned so far. You can go ahead and just simply expand this binomial. So remember our binomial rules. So we have 1 squared, so we have 1 minus 2 u squared plus u to the 4th power. Then we need to multiply the other u squared. So we have u squared minus 2u to the 4th power plus u to the 6th power. Alrighty, don't forget that negative in the front. So we have negative u squared minus 2u to the 4th power plus u to the 6th power. And then we can go ahead and integrate. So we have u to the 3rd power divided by 3 minus we have u to the 5th power divided by 5. That 2 coefficient stays. Plus u to the 7th power divided by 7 plus c. Let's replace u and distribute that negative. So we have negative 1/3 cosine of x plus 2 over 5 cosine to the 5th power of x. That was a cosine cubed. Minus 1 over 7 cosine of x plus c. Not so bad, right? So what we're going to keep doing in this section is keep working with different examples and see different types of situations. Not all of them can be solved using the Pythagorean identity, and not all of them will work with sine and cosine. So let's work with more problems. In the preceding examples, an odd power of sine and cosine enabled us to separate a single factor and convert the remaining even power. If the integrand contains even powers of both sine and cosine, this strategy fails. In this case, we can take advantage of the following half-angle identities. So these are our half-angle identities. Why are they nice? They're nice because it lets us get rid of that exponent. Now, before, we were able to get rid of the exponents in Pythagorean identities, but we had an extra, like a sine or cosine left over, so that it could be that our du with a u sub. But when you have an even exponent, we need to take a different route. Notice that all of our previous examples had odd exponents. Okay, so we have the integral from pi to 0 of sine squared. Okay, our problem here is our sine squared. Remember, if we're thinking our u is a sine, our du would be cosine. So we need to get rid of that square. We can get rid of that even exponent using our half-angle identities. So we see that sine squared can be written as 1/2 times 1 minus cosine of 2x. All right, let's make that replacement. So the integral from pi to 0 of, let's make that change, 1/2 times 1 minus cosine 2x dx. Alrighty, let's go ahead and move that 1/2 forward. We have the integral from pi to 0 of 1 minus cosine 2x dx. All right, we can go ahead and now take our integral of each one separately. So we have 1/2 the integral from pi to 0 of 1 minus the integral of pi to 0 of cosine 2x dx. Let's integrate. So we have 1/2 times x minus, and you can use u sub. Hopefully you've done u sub enough so you can see what's going on here, right? So our integral will be 1/2 sine of x of 2x. And if you need that u sub, let u equal 2x, du equal 2 dx. We need that 1/2 to make up for it, right? Let me just write it. So we have 1/2 pi of 0 cosine of 2x 2 dx. That's your du, that's your u. Now you can go ahead and integrate. All right, now we can go ahead and distribute the 1/2. So we have 1/2 x minus 1/4 sine of 2x. We need to evaluate from pi to 0. Once we work out the algebra, I'll let you do that part. We get 1/2 pi. Now again, for this one, we had to use a different approach because we had an even exponent. And we can do this with any number of even exponents. So we might have to repeat it more than once, just like in our following example. So here I have cosine to the 4th power. So for this one, we're going to use our half angle formulas twice. Let's go ahead and get started. So we have our integral of sine squared of x squared dx. We can go ahead and use this as our sine of x squared and replace that. Okay, so using our half angle identities again, we have the integral from 1 minus cosine of 2x divided by 2 squared dx. All right, let's go ahead and square, right? We have to square, which we have to use binomial theorem for our numerator. So we have to square it. So we have 1 minus 2 cosine of 2x plus cosine squared 2x divided by 2 or by 4 dx. You can factor the 1/4 out of our problem or our integral so that we have 1 minus 2 cosine of 2x plus cosine squared of 2x dx. So with this cosine squared, I need to use the half angle formula again. Let's go ahead and do that. So that we have 1/4, 1 minus 2 cosine of 2x plus, let's go ahead and do that. So we have, what is our half angle formula? So we have 1/2, and if we have an x, we're going to take the twice of that x. So here we have 2x, so twice of that would be 4x. So we're going to have 1/2 times 1 plus cosine of not 2x, but 4x, right? Because we're multiplying whatever was in that argument by 2. All right, let's clean that up. So we have 1/4 integral from 1 plus or minus 2 cosine of 2x plus, let's distribute that 1/2, 1/2 plus 1/2 cosine of 4x. And now we can go ahead and integrate each one separately. So for our answer, we have 1/4 times the integral of 1 is x minus, then we're going to have sine of 2x. And that's u sub, right? Plus, we have 1/2 x plus u sub again, 1/8 cosine of 4x plus c. We can go ahead and combine those like terms, and we get 1/4 times 3/2x minus sine of 2x plus 1/8 cosine 4x plus c. Okay, let's read from our textbook. What's a strategy for working with sine and cosine when they're both in our integral? To begin, if the power of cosine is odd, whenever you have 2k plus 1, that means odd, because you multiply it by 2, it makes it even, plus 1 more, you make it odd. That's what that means. If you ever see 2k plus 1 or 2k minus 1, it just means an odd number. So let's begin with this again. If the power of cosine is odd, n equals 2k plus 1, save one cosine factor and use cosine squared equals 1 minus sine squared x to express the remaining factors in terms of sine. So that would be like our first and second example. Then we use substitution with sine. B. If the power of sine is odd, save one sine factor and use the sine squared equals 1 minus cosine squared to express the remaining factors in terms of cosine. Then substitute u for cosine. And C. If the powers of both sine and cosine are even, use half angle identities and use that to get rid of that exponent. Now, everything we said also applies to tangent and secant. So we'll write that note above. This also applies to tangent and secant. Now, why tangent and secant? And it's mainly because their derivatives are kind of dependent on one another, just like our derivatives are sine and cosine are dependent on one another. So we're going to work on the next example that asks to evaluate the integral of tangent to the 6th power of x times secant to the 4th power of x dx. Now, as we work with this problem, it looks kind of a bit of intimidating, but it's not so bad. Let's just remember some helpful integrals. So let's recall that the derivative of tangent, so we have d dx of tangent of x. And again, these were given from your Calc 1 course, and the ones that weren't were developed in the last couple of sections. So derivative of tangent is secant squared x. The derivative of secant is equal to secant of x times tangent of x. And if we know derivatives, we also need to label their integrals. Now, the integrals we saw, they're not always straightforward. So the integral of tangent is the ln. Well, let me write it the way I have it in my notes. The integral of tangent of u du is equal to the ln of secant of u plus c, and the integral of secant of u du is equal to the ln of the secant u plus tangent u plus c. Okay, with that in mind, let's look at the next example. Evaluate the integral of tangent to the sixth power times secant to the fourth power of x dx. Okay, well, I see I have secant squares, and we also see that our derivative for tangent is secant squared. So we can easily use u substitution as long as I reserve a secant squared for my derivatives. Now, we only need one secant squared, but we have secant to the fourth power. Recall your Pythagorean identities. All right, so let's break this down. So we have tangent to the sixth power, that stays the same, times we're going to split secant into two different products. Secant squared of x times secant squared of x dx. Now I'm going to use one secant as a Pythagorean identity, so that we have tangent to the sixth power of x times 1 plus tangent squared of x, and we'll keep 1 the same because we need it for our derivative. Okay, now we can proceed using u substitution, where we can let u equal tangent, and our partial derivative, our derivative of tangent, you said was secant squared. Cool. So we see that we have our du is right there, and we can replace all of our tangents with u's, so that we have the integral of u to the sixth power times 1 plus u squared, and secant squared dx turns into our du. Now we just have to go ahead and distribute before we integrate. So we have the integral of u to the sixth power plus u to the eighth power. Remember to add your exponents. Du. Now we may integrate. We have u to the seventh power over 7 plus u to the eighth power over, plus 1 is 9. So u to the ninth power over 9. Let's replace u with tangent. So our final answer becomes 1/7 tangent to the 7th power, or tangent divided by 7. However you want to write it is fine. Plus tangent to the 9th power divided by 9. Because it's an indefinite integral, we need that plus c. Not so bad, right? Okay. Let's do another. Now we have find the integral of tangent to the 5th power times secant to the 7th power of theta d theta. Note, because of the odd powers, when we use Pythagorean identity, we're left with a tangent and a secant. And that works for our advantage because what's the derivative of secant? So let's write that down. So we should be thinking, okay, if we're going to use u substitution, what's going to be our du? So we need that derivative, right? Okay, so let's go ahead and break them into paired exponents so we can use our Pythagorean identities and have them under one single trig function. Now, since derivative of secant is tangent and secant, we need to make an effort to change that tangent into secant, because I'm going to want to make my u my secant. All right, so let's make that change. let's change tangent. So I have tangent to the 4th power times tangent to the 1 power. So we have our 5 tangents. And secant to the 6th power, well, we have theta as not x's. Theta, theta, theta times secant of theta d theta. Okay, now because we have our even powers, we're already thinking our Pythagorean identities. Well, not for secant, but for tangent. So we can think of that one as secant squared theta squared. And with our Pythagorean identity, we have I'm going to try tangent. I got ahead of myself. We can think of tangent to the 4th power as tangent squared squared. And we can use a Pythagorean identity to have secant squared theta minus 1 squared, or secant to the 6th power. And remember that tangent and secant that were left over? We'll write them together. You don't have to write them together. Remember, everything's being multiplied. I'm just setting myself up so I can visually see my u substitution. Alright, so if I let u equal secant of theta, the derivative, our partial derivative, will be secant of theta times tangent of theta d theta. Alright, so we have our du. We can replace everything with u. We're going to have u to the 6th power and u squared. So we can make that replacement, and we're left with u to the 4th power minus 2u squared plus 1 times u to the 6th power, and all that other stuff turns into du. Alright, let's go ahead and multiply. We need to go ahead and multiply that u to the 6th power. Remember, when multiplying, your exponents add. So our integral is now u to the 10th power minus u to the 8th power plus u to the 6th power du. Let's integrate. 10 plus 1 is 11. Divide by 11. 8 plus 1 is 9. Divide by 9. 6 plus 1 is 7. Divide by 7. Let's replace our u's with our secant, what it actually means. So our answer is secant to the 11th power theta divided by 11 minus 2 secant to the 9th power theta divided by 9 plus secant to the 7th power theta divided by 7. C. Wipe the page. Plus C. Alright, and there we have this problem here. Now again, what made this problem different is that we had odd exponents with tangent and secant, but that wasn't a problem because we knew that a derivative would involve both tangent and secant. Moving forward. Strategy for evaluating tangent and secant power integrals. If the power of secant is even, n equals 2k, that just means even. Save a factor of secant squared and use secant squared equals 1 plus tangent squared, a Pythagorean identity, to express remaining factors in terms of tangent. And use your u to be tangent. So remember, you're going to save a secant squared because our du is secant squared, right? That's the strategy. B. If the power of tangent is odd, m equals 2k plus 1, save the factor secant and tangent. We can use a Pythagorean identity for tangent squared to express the remaining factors in terms of secant, and then we can let du equals u equals secant, and this our du be tangent and secant, right? So that's what you want to save. It all comes down to what you want to save. And each one's different. And even though we have these pieces of advice, sometimes we just need to try doing a problem and see how far we get. And if we make a mistake, well, that's okay. We can always erase our work. All right, another example. Find the integral of tangent cubed dx. Okay, so we need to have that tangent squared. So let's rewrite it as the integral of tangent squared of x times tangent of x. All right, and we're doing this because we want to incorporate our secant squared. So now we change tangent squared to secant squared of x minus 1 tangent of x dx. Okay, so what are we looking for? You might start thinking u sub, but it's not really helpful. Because, well, you could, but that 1 is still in the picture, and that 1 is giving us trouble. Luckily, we can go ahead and multiply tangent. So that we have the integral of secant squared of x times tangent of x minus tangent of x dx. Now we can go ahead and use our u sub. Now remember, with that operation, that minus, we have two different integrals. We can write as two different integrals, and sometimes that makes our brain help us like decompartment, like put everything into smaller compartments. So we have secant squared x tangent x minus integral of tangent of x dx. Now we know the integral of tangent, and we know that the derivative of tangent is secant. So we can use u sub for our first part. So if we let u equal tangent of x, du equals secant squared of x dx. And this one we can just integrate by our formula. We were told where our integral is. It's given. All right, so that we have, for our first integral, we have u du, since that's our du, and that's our u, minus, and we have the integral of tangent of x dx, which is given. We'll just write it down. Let's go ahead and integrate. So we have u squared over u minus, our integral for tangent is the ln of secant of x plus c. Let's replace u, and we have 1/2 tangent squared of x minus ln secant of x plus c. All right, there we have it. Now, another helpful identity is one of our double angle identities. That's not double angle, it's product to sum. So the product to sum is helpful because when is this a problem? This is a problem we're integrating and we have different arguments for cosine and sine. And they're being multiplied. Well, I can go ahead and write them as two different integration problems of the same trig identity, so I can just work with each one separately. Let's see an example so we can make sense of the words just came out of my explanation. All right, so we have evaluate sine 4x cosine 5x dx. Where's the problem? We have a sine and a cosine, we're great. We're great, right? Well, we're not. Well, if we let u equal sine, and this is why it's wrong, right? So this is why it doesn't work. It doesn't work because if we let u equal sine of 4x, our du would be cosine of 4x times 4. We don't have cosine of 4x, do we? Mm-mm. So we have to use an alternate way. I can't work with sine and cosine being multiplied, but I can work with only sine as different terms and as a term itself. So let's go ahead and use our, what are they called again? Our product to sum and sum to product identities. Okay, so the one we're going to use is the one that says sine times cosine, and you have a choice. You can have only sines, you can have only cosines. It's your choice. We have a sine times cosine, so our options are A and B. Which one do I use? It's up to you. I'm going to use the first one. So we have, if we make that change, we have the integral of 1/2 times, okay, so we have sine of A, so A is going to be our 4x, and cosine is our B, so B is going to be our 5x. We have sine of A minus B, so 4x minus 5x, plus sine of A plus B, so 4x plus 5x. And I know you can do this mentally, I just don't want to lose anyone. Let's clean that up. Then move that 1/2 in front of the integral. So we're left with sine of 4 minus 5 is -1, negative x, plus sine of 4 plus 5, 9x. Now remember, sine is an odd function. So if my argument inside is negative, then we can move that negative forward. Let me jump back to the beginning and see why that is. Right, we have our sine is an odd function. Okay, jumping back to our example. So we can move that negative forward so that we have our integral of 1/2, and I can split each one as their own integral because each one is a term. So we have the integral of negative sine of x dx plus the integral of sine 9x. And I'm sure you know this without having to write the integral notation for each term, but it's just so you keep track of what you're doing. Each one is its own integration problem. So the integral of sine gives us cosine. So we have 1/2. This right here gives us cosine of x plus this right here, chain rule, we have 1/9 cosine of 9x plus c. And there we have it. Now I do want to incorporate another example because we can also be in a situation where we have to use integration by parts, section 7.1. So I'm going to erase this last example and use a space to use one more example that I forgot to include. So the other example I want us to do is, let's find the integral of secant cubed of x dx. All right, so we're working with secant, we want to incorporate tangent, right? So let's go ahead and separate our secant cubed as secant squared times secant. All right, we do this so we can replace this with that 1 minus tangent squared. As you work this out, you would see it wouldn't be really helpful, but we have two different arguments being multiplied, so we can continue by differentiation by parts. All right, we can let our secant be our u and our du be secant squared. All right, remember one of them you're going to take the derivative, the other you integrate. So we have du is equal to secant times tangent, and our, that's supposed to be a b, and our dv, so that our v is now our integral, which is just tangent of x. Now we can go ahead and integrate by parts. So let's write down the formula. Our formula is our integration of u and dv is u times v minus our integral of v and du. Let's make that replacement. So our u is secant, right? U is secant. So I have secant of x. Our v is tangent, minus our integral of u. What is u? Tangent of x. That's a v, not a u. Tangent of x. And our du is secant times tangent. Okay. Now, we see here that we have tangent times tangent. Tangent times tangent. Let's write it as tangent squared. So that we have secant of x times tangent of x minus our integral of tangent squared of x times secant of x. What is tangent squared? Our Pythagorean identity, that's 1, negative 1 plus secant squared, or secant squared minus 1. Let's make that change. All right, let's distribute our secants. Why are we doing this? Because we see that we're going to get secant cubed again, just like our initial one. So this integral is actually an integral that's going to keep you going in circles using integration by parts. So how do we do that circle? Undo that circle? Well, we can go ahead and break it up. So let me write this one more time. Secant squared times secant is secant cubed of x minus secant of x. And our integral applies to each term. So we really have secant of x times tangent of x minus our integral of secant cubed of x minus our integral of secant of x. Now, when you see that you have the same integral that you started off with, you set it equal to itself. So this is equal to secant cubed dx. You freaking write dx. So remember that trick we did in our section 7.1 when we have a problem where it just so happens that you're in a situation where you're going to be going in circles. Well, we can go ahead. We have an equation. We're going to add it to both sides. So add secant cubed of x dx to both sides. You add the same. So you have two copies of it. So you have 2 secant cubed of x dx. To get rid of the 2, you multiply it by 1/2 on both sides. So that you have 1/2 times secant of x times tangent of x minus, that integral is gone because we subtracted it out or added it out. And then we can go ahead and actually evaluate that secant integral. It's given our integral for secant is ln secant of u plus tangent of u. In this case, it's an x. So that we have 1/2 times secant times tangent plus ln of secant of x plus tangent of x plus c. Now, in case you're wondering, how did this turn into a plus from a minus? Well, we're subtracting. We have a minus and we have this minus here. So we had to distribute that negative. That's how it turned to a plus. All right, so you might be wondering, how do I know which one is which? Well, look at those rules that we had in those boxes from our textbook. And if you're unsure, go ahead and try it. And if you get stumped, you can try a different method from the ones listed from our textbook. All right, email me your questions. Your homework for this section is 1 through 33, every other odd. Thanks.